All right, morning everyone. How we doing? Monday morning. Final push, final week. Last 2 days of class essentially, today and Wednesday. You have your test on Wednesday at 9:30 or from 9:30 to 11 a.m. And that's really it. That finishes up chemistry for the year. You do have a redox project that is due Thursday night at midnight, so everything's due then. It's better to get the project done before the test anyways. It's good review. We have 2 things left to do today in class. Sometimes I do it in one day. Today I'm just going to do it in 2 days. Just split it out. It's types of what we call electrochemical cells. Today is a voltaic cell. Next class is an electrolytic cell. Going to be quick, not a lot of slides. Lots of information though, so please take accurate notes. Homework, make sure you're doing it. That's the only way you get practice. You have your review books to do stuff through as well. Honors kids, you have the answers in your book. Regents kids, I will be posting answers probably maybe Wednesday for the Redux unit so that you can do some work and see how you're doing on those. All right, so here we go. Bell ringer. So here, you gotta do oxidation numbers just like always. So we're gonna write in oxidation numbers. I think this number shows up good. Calcium's by itself, so it's gonna be 0. Hydrogen's by itself, it's gonna be 0. Oxygen in the compound is -2 always, so both these cases they're -2. Hydrogen in this compound is +1, and calcium, because this is a -2, calcium's gotta be a +2. All right, so oxygen in this case is a spectator ion, so we cross that out. So here, calcium is going from a 0 to a +2. The only way you can do that is if it loses electrons. So if it loses electrons, it's oxidized. If it loses electrons, that means it gives electrons to something else. So it causes something else to be reduced. So this thing right here is the reducing agent. All right, so this is the reducing agent. I'm just going to put Ra. All right. If that's the reducing agent, then this thing here, which in this case is going to be water, but it's really just the hydrogen in the water, is acting as the oxidizing agent because itself is reduced. If you look at hydrogen's going from a +1 to a 0. The only way you can go from a +1 to a 0 is if it gains electrons. And if it's gaining electrons, it's causing something else to lose electrons, which means it's causing something else to be oxidized. So that's where that oxidizing agent, reducing agent comes from. Lots of good review in there. Lots of things being able to figure out oxidation numbers, what is oxidized, what is reduced, and we go on from there. Okay, here we go. Electrochemical reactions. These are reactions that do one of 2 things. They're going to take electricity to make a chemical reaction occur, or they're going to take a chemical reaction to produce electricity. So it's kind of going one way or the other. So they're using electricity to cause chemistry, or they're taking the results of chemistry to make electricity. All right, so we're going to talk about one kind today, this kind that makes electricity. It's taking a chemical reaction to make electricity. In next class, we'll talk about electricity causing a chemical reaction. All right, so generally speaking, these are called electrochemical cells, all right, using electricity and chemistry to make a thing happen or a reaction happen. All right. For both of these types of cells, there's 2 similarities or 2 common concepts. All right, for both types of cells, I don't know why it's taking so long. There's a saying that's the red cat gets fat. All right, we're going to learn about electrodes in this part today, where we have electrodes for a battery. Like what we're going to talk about today is a voltaic cell. A voltaic cell is a battery. A battery has 2 terminals. You know them as a positive end and a negative end. All right, but they are called the electrode, and they are called the anode and the cathode, which are 2 specific types of electrodes. All right, the cathode, which cat is short for, is where red occurs, which is reduction. So reduction occurs at the cathode. And if the cat gets fat, that means the cat's getting bigger, so the cathode's going to grow in size, or it's going to get bigger. All right, so we have our little red cat getting bigger. All right, the other half of it is the anorexic ox. All right, an is short for anode, which is the other electrode opposite the cathode. Ox is short for oxidation. All right, so the anode is where things are oxidized, and since it's an anorexic ox, it's getting smaller. All right, so for both of these cell types, the one we're going to talk about today, Voltaic cell, the one we're going to talk about next class, which is an electrolytic cell, reduction will occur at the cathode, and the cathode is going to increase in size. All right, and then oxidation will occur at the anode, and the anode is going to decrease in size. So that's where we get the anorexic ox from, and the red cat gets fat. And in both of these cell types, electron flow will always go from what is called the anode and the cathode. All right, the charges of the anode and cathodes are going to be different. That's where people try to sometimes get confused. So make sure you have to know that part of it, that the electrons are always going to flow from the anode to the cathode. Oh, sorry, early this morning, not waking up. Okay, so here we go. Voltaic cells. Voltaic cells, common name is a battery. So we're going to talk about basic battery setup. All right. Now, there's all kinds of batteries. There's, you've heard of alkaline batteries, lithium polymer batteries or LiPo batteries. All right. Dry cell batteries, lead cell batteries. All right. There's all different ways of going about it. But general speaking, what they're trying to do is they're trying to create a flow of electrons. All right. And like the slide previously said, the flow of electrons is going to be from the anode to the cathode. Okay, Voltaic cells, all right, we're going to make the old-fashioned copper top battery. If you've heard of copper top, the copper tops are Duracell batteries. They actually have copper on the top. That's why they call it the copper top. Now it doesn't look like copper. It's just plastic sheeting on the battery. But they are called copper tops. I don't have Duracell batteries. I was going to use it as an example, but I don't have Duracell batteries here at home, so sorry. Voltaic cells. This type of cell takes a chemical reaction and produces electricity. So this is going to produce electricity. So this is chemistry producing electricity. And you guys should know that because batteries are stored energy. All right, and that energy comes from the chemical reactions that occur. All right, we're going to make it with metals, all right, with two different metals. And we're going to use this table right here, table J. We're going to go back to this. Remember the reactivity series of metals. And since we're doing a copper top, we're going to use a copper. If we were in class, I'd build this battery while we're in class, but we're not there, and I don't have the materials at home. We're going to make a battery out of copper and zinc. You can pick any two metals on table J, all right? But you're going to be better off, and these don't have electrical potentials on there. There's better metals to make batteries than others. Lithium batteries right now are all the one of the higher price batteries out there. Lithium is the most active metal according to table J. All right, it does have one of the better cell potentials, which produces the amount of current going through the battery. All right, but lithium would work really well for a lithium polymer battery, which it doesn't use another metal, it uses a polymer. All right, polymers are plastics. We talked about those in organic. All right, so here we go. We got zinc electrode and a copper electrode. It's going to take me a minute to go through this. Normally I just write on this. I'm going to go through the clicks, and I just have to remember the clicks before I do them. So zinc and copper. So for these to work as a battery, we need to connect them. All right. Traditional drawing for chemistry is we're going to connect these two electrodes with a piece of wire. All right. And we have to flood them with a solution. All right, we're going to put solutions in them. We're going to put them, in a battery. It's usually not a liquid. Like in the batteries you're familiar with, it's usually a paste where you have ions suspended in solution. We're going to use a liquid here, so it's going to be a wet battery. In the copper electrode, you have to put a copper-containing solution. All right, so we're going to put, you don't have to, but for ease of our sake of what's going on, we're going to call it a copper solution. It makes the ions a little bit easier to follow. So we have copper sulfate in here. It could be any copper, copper chloride, copper nitrate, anything that would work that's not uber super reactive. All right, because we have copper sulfate over here, we're just going to use sulfate again, but we're going to, because this electrode's zinc, we're going to use zinc sulfate. So what that means is, in this solution here, purple will work, I think. All right, in here, and all we're going to write in is what we're concerned with. This is going to have zinc plus 2 ions. Because if you did the reverse crisscrossing, zinc has a plus 2 charge. And then in here, we're going to have copper plus 2 ions. All right, that's what we're concerned with. The sulfates in this case are what we call spectator ions. They're just there to balance the charge of the coppers. So we're just going to deal with what's involved. We're only going to deal with the zincs in the left cell and coppers in the right cell. We could make this battery where we put the copper over here and the zinc over here. We just have to flip everything, so it's fine. All right, so next thing, I believe we have to connect these with a wire. There we go. All right. So you have to connect these from the wire, you know, some type of metal or something that will conduct electricity. All right, and this is where we're going to look at table J, and this is where we figure out which one's the anode and which one's the cathode. All right, so we're going to look on table J, and you're going to find zinc and copper. I know copper is down at the bottom. All right, and then zinc is somewhere up above it. So zinc is more reactive than copper. Metals that are more reactive than another metal are the metals that are going to lose electrons. So the zinc electrode over here is going to lose electrons. Let me get a color that will show up. All right, so this one's going to lose. I'll try to write instead of clicking on it. It's fine. It's just going to be a little bit messier. But so the zinc electrode is going to lose electrons. So it's going to lose electrons through the wire. So it's literally, once these are connected, all right, there's a movement of electrons. And this is one of the biggest things that leads to corrosion for people that are interested in things like that. All right, when you make things out of metal, it's better to use the same metal because usually there's always going to be a cell potential difference, and it's going to cause one metal to corrode versus the other one. All right, so the electrons are going to move through here. These are actually, in this particular case, it's going to move through in chunks of 2 electrons because it makes a zinc plus 2 ion or a copper plus 2 ion. All right, so this is going to lose electrons. So if the zinc loses electrons, that means what happens to the copper? The copper is going to gain electrons. So I'm going to come over here and we'll just kind of build these together. And how do we figure out which one gains electrons and which one loses electrons? All from table J. All right, all from table J. All right, all from here. The one that's more reactive is going to lose electrons because more reactive metals lose electrons easier. The least reactive one is going to gain electrons. So the zinc electrode in this case is going to lose electrons. All right, if you lose electrons, are you oxidized or are you reduced? All right, so I think the first thing that I populate up here on the slideshow is lose electrons, table J. So, all right. Therefore, if it loses electrons, it is oxidized. All right, it is oxidized. I'm just getting rid of that so it's easier to see. All right, because loss of electrons is oxidation, gain of electrons is reduction. All right, as a result, the zinc electrode is oxidized, so it's losing electrons. All right. Now, because it loses electrons, all right, remember anode is where oxidation occurs. That makes it the anode. In a voltaic cell, the anode's the negative terminal. That is not the case for the one that we're going to do on Wednesday, but for today, the anode is negative, and just kind of like before, all right, I take the N in anode, meaning negative, and this is going to be the cathode. All right, it's got a positive sign in it, so the copper is going to be the positive terminal. All right, the anode's negative. All right, so what happens here? So let me get my purple because we're going to go back down to the cells down in here. Every time this thing loses 2 electrons up here, what happens is you're going to create a zinc plus 2 ion. That's going to be, it can be anywhere on this piece of metal. I'm just drawing it down here for convenience sake. All right, every time it loses 2 electrons through the wire, it's going to create a zinc ion, and the zinc ion is going to get kicked off into solution. All right, so you're going to see, initially, you're going to see a raise in the number of zinc ions, or more importantly, a raise in the positive charge in this solution. All right, over here, this thing is going to gain electrons. All right, now electrons cannot go into liquid. All right, liquids don't conduct electricity. There are ions that can conduct electricity, but liquids by themselves don't conduct electricity. So the electrons can't jump off into solution. Electrons can't do that. They have to conduct something or touch something metal or solid. So what happens, this is going to become temporarily negative, all right? And then, so let's say there's 2 electrons here. All right, I probably should put plus 2 electrons. And because this is a negative charge, it's going to attract the positive ion from solution. All right, and things are going to happen over here that's a little bit different than over here. Okay, so now what we're going to do, we'll click down through here. Oops, I didn't write that. I thought I typed the half reaction. So the hardest part about this whole thing is what's happening with half reactions. We have to write, excuse me, the half reaction that occurs here. So this is losing 2 electrons. So if I were to write I'm going to get yellow because it's easier to see. All right, so here we go. We got our little arrow. And if you're losing electrons, where do you put electrons relative to the arrow, the left or the right? If you're losing electrons, I'm going to put electrons on the right side here. Put 2 electrons here. All right, now it's got to be negative. Now what did I start off with? I started off with the zinc ion, or zinc atom. How do we abbreviate zinc atoms? Zinc atoms are Zn0, because 0 means it's an atom. So a zinc atom is going to lose 2 electrons, and as a result, it's going to produce a zinc plus 2 ion. So now if we look at this thing here, yellow's tough in here. All right, we got a zinc atom losing 2 electrons, turning into zinc plus 2 ions. Zinc's going from a 0 to a plus 2, which is oxidation, which makes sense because this is oxidized here. So this is our zinc oxidation half reaction. We've talked about half reactions here. All right, over here, this thing's gaining electrons, so since it's gaining electrons, it's going to be reduced. I'm just going to use the click because it's there. No, don't erase all ink, eraser. All right, so it is reduced, all right, because it's gaining electrons from the zinc because the copper is less reactive than the zinc. All right, because it's reduced, it's going to be the cathode. And then the thing that's unique is that the cathode in a voltaic cell, the cathode is going to be the positive terminal. All right, you can't figure out the positive by the charges of electrons. It doesn't make sense there. Okay, so now we have to write our half reaction over here for what's happening with the copper. All right, so we've got, so once again, I'm going to write my arrow. Now I'm gaining 2 electrons on this side, so I'm going to put the electrons on the left side of the arrow. So that's how I know it. All right, now what's gaining 2 electrons? All right, now is it the copper atom or the copper ion? All right, what the electrons are actually reacting with here is actually the copper atoms from solution. So you got the copper ions, or copper ions from solution. I said atoms, sorry. All right, you got Cu plus 2 electrons is going to turn into, now mathematically, what's that going to turn into? A copper atom. All right, a copper atom. So it's plus 2 electrons, Cu plus 2 electrons turn into copper 2 atoms. It's going from a plus 2 to a 0. All right, therefore, it's got to be reduced. All right, another way you can play the game to do this, you know that copper is going to be a plus 2. You know that the copper atom is going to be a 0. Which way is reduction? 0 to plus 2 or plus 2 to 0? Plus 2 to 0 has to be the reduction side. That's kind of a way you can figure this one out as well. Flip side over here, you've got 0 and plus 2 for zinc. All right, but so for it to be oxidized, it's got to go from 0 to plus 2. And then you can just write the half reaction to make it sense. Now, this happens temporarily. Now, what's going to happen in this situation is every 2 electrons, this zinc electrode is going to kick off a zinc ion into solution. So every 2 electrons goes this way, you lose a zinc ion, zinc atom. All right, every 2 electrons over here, you lose this copper atom ion from solution. All right, these will run out. All right, as such. So you need something else in these types of cells to continue the reaction. This is just showing the electrons going through. I tried to do all right, this will not go on forever. Oops, I'm going to go back because, actually, I'll leave that there. All right, so here's the same thing right here. Now, what has to happen for this to continue is we need this big green thing here. This big green thing here is called a salt bridge. Hopefully, I populated it up so I don't have to type it. All right, it doesn't matter what salt is in the salt bridge. All right, I didn't populate it. All right, it doesn't matter. So salt bridge. So I'm just going to write salt bridge. Salt bridge is extremely important. Definition of salt bridge is extremely important. All right, guaranteed question on the test, guaranteed question on homework tonight. What does a salt bridge do? Salt bridge does one thing, permits the flow of ions. It does not permit the flow of electrons. Remember, electrons cannot go through solutions. All right, ions can, electrons cannot. So the salt bridge in this case here is this green thing. All right, how the salt bridge is accomplished in an actual battery is they're all different ways. All right, usually it's a permeable membrane that lets certain things through and not others. But the salt bridge does one thing and one thing only. It permits the flow of ions. And this is going to look really bad. Permits the flow of ions. Might be the worst writing. Now you guys know what I look like or what I have to read on tests. Permits the flow of ions. All right, salt bridge has one function. Does not permit the flow of electrons, permits the flow of ions. Electrons flow through solid material, ions flow through solutions. All right, and what this does, and luckily for our level of chemistry, we're not going to go into the actual charges, but all we're going to say is it maintains neutrality between these two, because remember, what's happening at the zinc electrode? It's losing electrons. All right, which means it's kicking off positive ions into solution. I'm just going to get this into red. Or no, we did purple over here. So you got these purple ions over here. You got these zinc ions that are coming off because you're gaining that. You're kicking them off here. All right, and here the copper has got these ions that when the electrons come over, the copper ions are going to be attracted to the electrons. They're going to make a copper atom. So this electrode is going to get bigger. This electrode is going to get smaller. All right. So what happens is what's in the salt bridge is a salt. It's an electrolyte solution. All right, which is just going to maintain neutrality. All right, when you get to superchem, they'll talk about which way the ions move. I'm not going to worry about which way the ions move, but this one's becoming positive. This solution's becoming negative. So you're going to get a flow of ions through here. We're not going to. All we have to know about salt bridge maintains neutrality. All right, it's there to keep the reaction going. What causes a battery to die? Batteries die when this thing runs out. All right, when the anode runs out of material, all right, it dies. It stops working. If you have a rechargeable battery, like your cell phone, when you plug it in, all that plugging it in does, well, in a very simplified form, is that instead of electrons flowing from most reactive to least reactive, the plugging in or charging part reverses the electron flow. So now the electrons are going to go from, in this case, from right to left. So this is going to gain electrons, which means it's going to pick up an ion from solution to make an atom. So this is going to grow in size, and then this is going to decrease in size. And when it's fully charged, it gets back to its normal starting conditions. You can use your phone or your electronic device, and it reverses it just goes normally. Electrons are going to flow from left to right, goes over here, and goes, and then when you charge it, electrons flow from right to left, and the whole process is reversed. That's what that's all a rechargeable battery does. There's some things, some considerations in there that you have to worry about, but on a very simplistic level, that's what's going on. All right. I think that's it. All right. Okay, that's our bell ringer for next class. So that is done. There's a lot of stuff in this. All right. I would highly recommend trying to do these notes. Try to build a cell yourself. Just pick 2 metals off of table J, and then try to go through everything else and then compare it to your notes. Very important stuff here in real life, actually, and what they do stuff. Okay, have a great day. We will talk to you on Wednesday.